I start by introducing our work. Our work is on AraBERT, the Arabic, the first version of the BERT model for the Arabic language. It was a project that I started with my friend Fadi Bali and my advisor Dr. Hazem Haj. Let's skip about me because Noura did a great introduction. And the outline for today is I'm going to be explaining a bit about transfer learning in NLP and how it is applied in NLP in general. And then I will introduce in a simple way the transformer and the self-attention architecture, which are necessary to understand the BERT model and how BERT understands language in general. Also, after it, I will introduce the BERT architecture. I would explain the inputs, the outputs, how did they do the pre-training, how can we fine-tune it into our own data and tasks, how BERT handles input tokenization. I will also show you a demo about the pre-training of BERT. How can you see the outputs of BERT? How can you interact with them? After that, I will introduce our work on the Arabic version of BERT and what's the difference in tokenization, how did we do the pre-training, what was our data, and I will also explain our results, how did we achieve them, what are they, and I will finally show you a demo about how can you use AraBERT for your own data. So a primer on transfer learning. Transfer learning is a technique in machine learning and in deep learning where if you have a large data set, let's call it here data set 1, you first train a model on it. This model will acquire some knowledge from this data set. And using this acquired knowledge from this model, we can later on train it on a new data set, which is different from the first one and usually a smaller one. So the transfer here is about transferring the knowledge from model 1 to model 2 here, and this knowledge is field dependent or task dependent. So it varies from a field to another. And usually the model 2 will require less data, less labeled data, and will have a better final performance since it gains some information from the knowledge that was gained from model 1. And you can also think about it as if model 2 was initialized, its weights were initialized from model 1. So model 1 will have to be a general model, or will have to be a model that was trained on a similar task to model 2. So that this knowledge can be transferred from model 1 to model 2. In NLP, we usually train a model 1 on a large unlabeled data set, which are usually Wikipedia articles, news articles, or recently conversation data. Just it's unlabeled, or we cannot call it unsupervised because technically the labels are within the text. So we call it self-supervised. So our labels are within the text, and you'll see in a bit what do I mean by that. So the model 1 will acquire knowledge about the language or about the semantics behind the language that we train on. So if we train on English, it will understand subject-verb agreement. It will try to understand the gender. It will understand relations, hyponym, synonyms. It will gain some general understanding about the language. We can then use this model and train it on our own data set with our own tasks. So let's say we have a task on offensive tweet detection. So we usually have small data sets here compared to the large unlabeled one, and we can use this model that we initialized with the training on the large data set, and then we fine tune it on our own data set that is usually labeled, and we call this supervised learning here. And at the end, we will generally get a better performance. And also we have faster training. So because we already initialized our model, the second model, we already initialized it from the knowledge of the first model. And this is generally how transfer learning works in NLP. The idea behind transfer learning for NLP came in, it was first used in the embedding layer, where we usually we usually take these pre-trained word embeddings and we just plug them in the first layer of our model, and that's it. So we use whatever knowledge was acquired by the first layer, which is just the embedding of the word, just a meaning of the word. It probably has zero context about this word. And then we plug it in our, so we use this word embedding as features, and we plug it in into our classification model. But in 2018, a new paper by Sebastian Ruder and Jeremy Howard, so it's called the ULM Fit paper. They introduced a new kind of pre-training and fine-tuning, a new kind of transfer learning for NLP. So instead of just taking the word embedding layer, why don't we take the whole model with all the layers in it, and we use the whole model for a new task? So by that, I mean that we first have to find a pre-training task to train our big model, and they call it a universal language model because the universality here is about having this model work on multiple tasks. So we'll have to find a pre-training task. The easiest one is language modeling, which is like predicting the next word. So it's just like your keyboard, your mobile keyboard, when it tries to predict your next word, but it's more sophisticated than that. So you feed it data from, let's say, Wikipedia again, a large data set. They did the ULM fit on I think Wikipedia. They started by getting sentences. The training data was then extracted from these sentences by hiding as a word and relying on the word before it to predict it. And this is how the model gains information about a certain language, let's say. So instead of using just the first layer here, we use the whole model on our training, on our own tasks. So let's say our task is movie review, sentence analysis on movie reviews. So here we have a new domain for our language. So the vocabulary used in our movies is different than the vocabulary used in Wikipedia, and it's different from the vocabulary used in our news articles. Sometimes it varies a lot. Maybe I'm using vocabulary. My data set here is from the medical domain, so there will usually be a very little overlap in the vocab. So for that, I have to also continue the pre-training of the first model that I do. I do the same task on my new data set, my smaller one. So I adapt my language models to the new domain. So here, before I had like a sentence, the quick brown, I have to predict fox after it. In the second phase, the adaptation phase, I have a sentence which is like Avengers is a good movie. I have to predict movies, so I gain knowledge about that Avengers is a movie, and Avengers, maybe it's from. I'll get info about the DC universe, the Marvel universe, and this stuff. So it's stuff specific for our new data set. And at the end, because I'm interested in predicting the sentiment of a movie review, I have the movie review, I have the label. I will feed it in. I will feed in the whole sentence this time, so I don't mask anything. I don't hide anything from the model, and I fine tune it on our on these labels. And at the end, I should get the positive sentiment or a negative sentiment. And how is this done specifically for BERT? We will get into it into our fine-tuning section. So the modern NLP, in the modern NLP era, we have like a general model types. The most popular of them are all transformer-based models, or actually BERT, not BERT-based, but because BERT is based on the transformer, so these are the BERT and transformer models. Another one is the GPT-2 model, which you might have heard about, released by OpenAI, that said that it was a model too dangerous to release for the public, and they waited a year for people to be able to identify if this model generates fake news, or they can. So the model, so there is another model where to be able to identify if the GPT-2 was if the output of this text is a GPT-2 made output, or it's a human made output, because the humans weren't able to differentiate between them. and that's why they were afraid that it might be used to automatically generate fake news. So it makes the whole stuff harder for social media. So also we have the Elmo model, which is, it came right before the transformer model, but sadly the transformer model got all the attention, and pun intended, I think. So the transformer model got all the attention, and we continued using this architecture. So what's the, I disable this. So what is this transformer architecture that I was talking about? It's just stacking some encoder layers. So it's stacking some encoder layers that are based on self-attention. And it was made for machine translation, which is based on a sequence-to-sequence model. A sequence-to-sequence model is a model that gets a sentence as an input, encodes it into a context vector, let's say. This context vector should carry the meaning of the input sentence. So let's say here I'm doing translation from French to English. I have to encode the meaning behind the sentence "Je suis étudiant" into a context vector here. And using this context vector, I have to now generate a new sentence, but in English. And for that, the transformer architectures stacks encoder architectures on top of each other, and then it uses a decoder. Also, it stacks a decoder architecture and to decode this context window. So, what's this encoder architecture? The encoder architecture is based on a new layer that the authors of the transformer model, Vaswani, introduced. It's called the self-attention layer. I will explain it in a bit, and then after that they add some normalization and the layers. So an encoder block is essentially a normalizer and the feed-forward layer, and they stack them together. The original transformer model, they stacked 6 layers as encoders and 6 as decoders, and each word was also a vector. So this self-attention works on vectors. So self-attention or generally the multi-head self-attention. This beautiful equation here, which if you look at it, you can generally understand that you are trying to find the dot product between a query and a key, which is both of them here are the same input sentence. So imagine if I have this input sentence here and I have this output sentence, the same input sentence here, I mean. And if I multiply the embeddings of these two sentences by each other using the dot product, I will then find the similarity between each token and the other tokens. So in essence here, if I have, let's take the word "it" here, I will make the model learn that to which other words the word "it" is referring. So here it will try to understand. It should understand that it was referring to the animal. In the sentence, the animal didn't cross the street because it was too tired. So it was referring to animal. So the weight here, the dot product between it and the animal should have a bigger value. So this is the general idea behind the attention. We are training our model to understand the relationship between these words. We also have some scaling and some value vectors, but the general idea here, I'm not really going to get into them now because they'll take some time. But the general idea is that the self-attention mechanism tries to force these vectors to find the representation that carry the meaning of this word, looking at its context. Also, we can see here that the word "it" is finding the context to its left and to its right. So it's looking at the whole sentence, not only on the left of it or on the tokens that came before it, which are the language model architecture that I talked about earlier. Tries to find a better representation for this word "it" based on the context that it is on. They stack these. We stack multiple attention heads, so we don't get only So the model doesn't only focus on one part of the sentence. The sentence was too long, and it also has some good mathematical properties that make it easy to train these models. Another advantage for the self-attention model over the previous LSTM models and RNN models is that it's easier to train. It's easier for the hardware to train because almost all the operations here are parallelizable and they don't have time dependency. If we take an example for another RNN, I have to propagate my gradient through time back in the sentence. So I cannot calculate the gradient of animal before I finish calculating the gradient of the word because, which limits the parallelization capability of my model and makes the training takes much more time. This is the second main driver of the transformer architecture. And Google was behind the transformer architecture and behind a unit that trains the models, the TPU unit, which is a unit specially made by Google to train machine learning models fast. And this benefits a lot from the architecture of the TPU, the tensor processing. So what does BERT have to do with all that? BERT here, instead of relying on an encoder-decoder architecture, BERT is simply the encoder part. So BERT only stacks encoders to get a better representation of this sentence. And by having better representation of the sentence, we can then later do some classification on top of this representation, and it can benefit us for multiple tasks. So the BERT architecture was also released by Google research team. It stands for bidirectional encoder representation from transformers, and it's also a pun intended for the Elmo paper, the Sesame Street characters. But let's just ignore that a bit. And by bidirectional, they mean that each token will look at its left and its right, so to understand all the context of the word instead of just looking at the word before it. The encoder is the encoded part of the transformer. And they initially released two models, a base model and a larger model, which is of course better. The base model had 12 layers instead of the 6 layers in the transformer. And each layer had 12 attention heads. The embedding dimensions were 768. And in total, it was a pretty big model. It had 110 million parameters. And the large one had 24 encoder layers, 16 attention heads, and 1,024 embedding size, for a total of 300 million parameters. So this BERT architecture will take as input a sentence or tokens. So it will take as input word tokens. These word tokens, we also append to it a CLS token, just the CLS between brackets. I will talk about it later and why we are using this CLS token. And we feed it throughout these encoders, these stacked encoders, and each encoder will learn something about this sentence. So maybe the first one will learn about the local language understanding. So what's the relationship between prince and help? The second encoder maybe will learn about a larger understanding of the sentence. It will learn about the relationship between sentence segments, and so on as we stack encoders. Why 12 encoders or why 6 encoders? I think Google research team tried multiple parameters, and 12 came up to be one of the best. They also recently released all the smaller models, and it turns out that 12 layers are the best for them, for this architecture. We can go higher, but 12 was good enough. Also, 12. Why do we have 12 attention heads? This is also not set in stone. Some research was done about pruning this head, so just deleting some of the heads, and the model retains some performance because some of the heads learn the same thing, so it's like redundant parameters. So we don't really need them, but it's still a research area. So the input here are again a sequence of words, and the pre-training task is just simple. Instead of language modeling, which is predicting the next word, we have to mask some word inside our sentence, and the model will try to guess what word was it. And by that, it requires understanding of the left and the right context of the word. So it doesn't just like look at its left; it will look at the left and the right context. And we don't need labeled data because the labels are within our data. So we get our sentences, our document, we split it into sentences, we take some words, we mask 15% of the words by a mask token, and the label, we extract the label. The model will have to predict what was it. So it might have multiple predictions, like the sky is sunny and hot, it doesn't work. The car is sunny and hot, also it doesn't work. But the weather is sunny and hot, this will work. So this will have a better probability of being here. And the model will have to learn that. So the initial BERT was pre-trained on the English Wikipedia and the book corpus, which is a total of 13 gigabytes of text. And they also released another multilingual model, which was trained on all the Wikipedia for 107 languages, including Arabic. So this, I think, was the first time that we saw some attention to the Arabic language. And even though it was trained on 107 languages, it still performed well on multiple languages. Mainly because some languages are similar. So if you take Latin languages, they share the same vocabulary, the same letters, sometimes the same vocabulary, the same sentence structure. So it can learn from French and English at the same time to have better prediction on English, let's say. And they trained this model for 1 million steps or 1 million gradient updates on their own TPUs. The training lasted for 4 days, so it takes a lot of time and a lot of compute power to train these models. And here you can see again another illustration about the BERT pre-training. By the way, these illustrations that I'm using today are from a blog by Jihad Al-Amar. It's a great blog, and it's used everywhere in the NLP community. The illustrations are just too good. And the explanation there, it's also too good if you want to understand more deep how the BERT and how the transformer model really works. Also, another task that the model introduced, which is the next sentence prediction task. And they introduced that along with a CLS token that I previously talked about. So in each sentence, we first append the CLS token at the beginning of this sentence. And this token will learn about the relationship between two sentences. So it's a two-sentence task instead of a one-sentence task. So let's say here we have the BERT paper suggested that we use a next sentence prediction task, where the model tries to predict if sentence 2 really came after sentence 1, or it's not from the same, not a sentence from the same document. So if I have a document, I split it into sentences. The labels I will replace some sentences with a random sentence from other documents, and the model has to predict if the second sentence came after the first, yes or no. Well, I will also mask these sentences. So I'm doing two tasks at the same time. I'm doing masked language modeling and next sentence prediction. The benefit here from next sentence prediction is that the model will learn dependencies between two sentences, which is useful in some benchmark tasks that require two sentences as input, such as extractive question answering. So you feed it a question here and then answer in the second sentence or the second passage, and the model has to extract what is the answer from this paragraph. So this is the second task. And I will show you now a small demo about the output of the masked language model of BERT. This. So here, by the way, I'm using the transformer architecture, the transformer library from the Hugging Face architecture. And I start by installing these two libraries that I will use for the Arabic. Here I'm demoing mask language modeling with our Arabic model. I will not run it now because it has to download a lot of models. I'm just showing you the output. Let me zoom in a little bit. So we install the transformer library and the other requirement libraries. We also I'm importing all Arabic-based models here, which are, we released two models, two AraBERT models, and I will talk about them later. There was another BERT model released by Ali Safaya from Turkey. Also, there are multilingual models released by the multilingual model released by Google and another this is a duplicate here, and another model released by Facebook AI, which is an XLM-based model. It also supports Arabic. So I'm testing here. I'm showing the difference between the AraBERT model predictions and the multilingual model predictions, and also the other Arabic BERT models. Again, I will not run this because it has to download all the models, and it will take some time, but these models are huge, especially the large one. From the transformer library, I'm importing pipelines, which are readily made codes that you can use for let's say sentiment analysis, question answering. So you just fill in what task you want, and it will configure itself on its own. You just give it what model you want and what was the tokenizer, and it will just give you a ready model so you can use. Again, I'm comparing between 6 models, our own 2 AraBERTs, the other Turkish, the other BERT made by Ali, the multilingual BERT, and the multilingual models released by Facebook AI. So here, let's see. Asimat, Lebanon, here, I'm hiding the answer. I'm hiding by the word mask. And this is the output. You see, by the way, the word mask should be on the left, but because we are mixing Arabic and English here, the output format is sometimes wrong. But trust me, it's on the left here. It's not on the right. So Asimat Lebanon, the model has to predict Beirut. And here's the code to run all. I'm running here all the models, and we will see the output of all our models. So the first iteration of our model predicted that Trablus was Asimat Lebanon, was the capital of Lebanon. And the second prediction, so I'm putting the top 10 predictions here. The second prediction was Beirut. It's close probability. And our second model predicted with more confidence, 60% confidence, that Beirut is actually the capital of Lebanon. The second Arabic model released by Ali fell short, so it predicted random words and it has zero confidence about them. I don't know why, honestly. The multilingual BERT came in a good position. The first time it predicted a column. Maybe it usually sees Asimat Lebanon here, a column, and then Beirut. And the second prediction was Beirut, so it's fine here. And Facebook released one, failed miserably. I don't know why, maybe because it had too many tokens to figure out. It was trained also on 100 language and I think 2 terabytes of data. So I'm not sure how the performance will transfer for Arabic. They showed some benchmarks, but not for Arabic. And the base one also fell short of predicting it. And this is how we trained the mask language model. So we hide a word, and the model has to predict it. All good till now? Anyone have any question?
Yeah. Can you talk a bit about the confidence in BERT? How is the confidence?
On this, well, you can think about it as confidence, or you can think about as what was the probability of the word here being Beirut. So the higher the probability, the more confident the model is in its output.
Yes.
Again, any questions before I move on?
Yes, I have a question regarding the tokenization.
Yeah.
Are all is the tokenization the same for all the models that you tried?
Only the last model. Okay, I will get into this a bit. Only the last model, the AraBERT V1 model, we do pre-segmentation on the words, and I will explain why we do that. The AraBERT V0.1 and all the other models don't do that. They just throw in the words, and the model should try to predict it. So here, if you can see here, the text that was used by AraBERT V0.1 and all the others wasn't pre-tokenized, wasn't pre-processed. So when we do pre-processing, we split for AraBERT, we split some of the words into segments. So it helps the model understand better understand the language, the Arabic language. I will get into a bit into details of this in the next section, after I finish talking about BERT. So to do fine tuning on BERT, we can use the CLS token, the embedding of the CLS token. So each token here is a vector of 768 dimensions, and this CLS token will contain the pooling mechanism of all the vectors. So it's like an attention over all the vectors. After that, we just insert a feed forward or a dense layer, and then we connect it to the output layer, and that's it. So we take the pre-trained BERT model. Here, let's take the task of a single sentence, which is that, let's say, sentiment analysis. We take the embedding of the first CLS token, which stands for classification token. We append over it a dense layer and train the model with the layer on it. And we only care about the output of this class label here. If you want to do sentence classifications using two sentences, which are some tasks from the GLUE benchmark, if you are familiar with it. So these are like predict if there is contradiction. So it's language inference tasks. These are popular tasks that are used to benchmark models. We can also use the same architecture. So we take the embedding of the CLS token and we append the feed forward layer over it, and then we can do classification. If you want to do question answering, so again, we feed the input question as the first sentence, and the paragraph as the second passage, or as the paragraph where we have the answer. And the model will have to predict which was the first token of the answer and which is the last token of the answer. So it tries to predict a span of the answer. And we do that by training also one. So we are classifying all these tokens as they are start, yes or no. They are start for the span, yes or no. And we also add one condition that the end should be after the start, which is logical. And that's how we can extract answers from an article. Please, if you didn't understand this, let me know. And if you want to do NER tasks, it's also a very common task in information retrieval. We can train also a simple feed-forward network, and it goes through all the tokens and it tries to predict the tag for each token. And I think this is implemented in the Spacey library. So with Spacey NER, it's implemented and ready to use. As far as the results, yes.
Excuse me. Can you please explain how to add the condition?
for the question?
The condition here, I think, in the code, if they first start by predicting which is the start span, which is the start token for our answer span. My internet, is it lagging or okay? Can you hear me well?
I think it's cool.
No, you're okay.
Yeah, because Zoom gave me a notification. So again, the model will try to first predict the start token, and then it will also loop over all the tokens. But instead of starting with tokens before the start token, we start with the next ones. So just this, that's the condition. So if the model predicted that an end was before the start, we just discard this prediction.
So this is like extractive question answering.
This is exactly
there is also
question answering.
Yeah, and also there is abstractive. So did you consider this as well, or
abstractive question answering? The Google researchers didn't consider this. Again, the BERT model isn't my model. AraBERT is based on BERT. So there are other models like there is one called BART, recently released by Facebook, I think AI, and there's another model called the T5 text-to-text transfer transformer. It's a huge model also that can do abstractive question answering. But this type of models here cannot do extractive question answering because they don't generate sequences. So to do abstractive question answering, you have to generate some output sequences, right? But here we only do classification. And this is a solution of like casting the question answering problem into a problem. All good?
Yes, thank you.
Yes, and when BERT was released, and this is the results, I think, on the GLUE benchmark, the results of the BERT had very high results compared to previous models. So this jump here was mainly caused by BERT models, and then later fine-tuning and iterating over the initial BERT architecture. So it made a very good jump in NLP results. And after that, recently Google released the AraBERT model, which is based on BERT but has smaller footprint and better pre-training tasks, and also some optimization in it. And we recently were able to beat the human level in these benchmarks. And you can look at the results in the squad benchmark, and in the GLUE benchmark, which is a general language understanding benchmark. The models were able to beat humans. So this needed creating new benchmarks for getting better understanding of these results. And one more thing about BERT, that we have a problem in NLP, which is the out of vocabulary words. So what to do if we don't have a word, if we encounter a new word that we didn't see before in our training, and we don't have it in our vocabulary? What to do with it? Usually they used to do replace it by a un character, UNK, or unknown token, or in machine translation they started using a BPE algorithm, which is an algorithm based on knowledge compression. And the whole of it, the idea behind it, which was also used in BERT, is that we first start by our characters. So let's say in English we have 26 characters, Arabic I think 28, and also some exclamation marks, the numbers, and these characters. So let's say let's just take the English characters. We start finding the most common combination of these characters. So let's see here that the word ding, or maybe sometimes ing, is common is very common in language. Maybe in the words like limitless, colorless, the word less is very common. So we split these words into color and less. If we didn't find the word colorless as a whole, we split it into color and less. And if we have a word that we've never seen before and it has nothing common with our vocabulary, you can, this is the worst case, you can just split it into letters or into like small combinations of letters, and the model will try its best to understand the relationship between these letters. So this is why when you train on a new domain language, or on let's say in the medical field, you have to sometimes do some continue this pre-training to make the model more used to the language that you are using. So you don't just like start do classification. You can start doing classification without continuing this pre-training if the domain is the same. But if the domain is very different, it's suggested that you continue some pre-training to make the model familiar with the language that you're using. And yeah, after that, I will introduce I will talk about how we did AraBERT. So me and my colleague Fadi Bali, which I believe is in the chat, we based our AraBERT on the BERT-based architecture. We gathered 3 billion words or 70 million sentences, which are a total of 23 gigabytes of text. These sentences, we got them from the Arabic Wikipedia, which is, I think it's about a gig or 1.2 gigs. It's smaller than the English Wikipedia. I think the English Wikipedia is 6 gigabytes. So we had to get the news articles, to gather publicly available news articles from datasets that are publicly available. We also did some web scraping over big websites, big news websites like Al-Akhbar, Al-Nahar, Al-Satir. And the data sets are all made of newspaper articles from all different regions of the Arab world, so that we can cover cities not just only from one country or from a couple of countries, so that the knowledge would be, so that we encode knowledge about the whole Arab region. This is our main intuition behind finding out all these, getting all these news articles. And we trained on also on Google TPUs, which the training took us 5 days to do it. And our models are available on our GitHub repository under the AUB Mind organization, which is our team at the university. There you will find the TensorFlow checkpoints for both AraBERT v1, which is the better one, and the first one, the v0.1. We also provide the PyTorch models pre-trained. Also, the PyTorch model, we added them to the Hugging Face repository. It's a famous repository for the transformers. So it provides a very good API to use transformers with them. So what we did different for AraBERT is that we noticed when we first did the v0.1, let me get into what we did before that. We removed all the diacritics from the AraBERT. Our intuition behind it was that we usually don't use diacritics when we read the language. We might need the shadda sometimes, we might need the tanween, but we can usually understand it without it. So you can usually read Arabic without the diacritics, because the data on the internet had some diacritics, but not all of it. So we decided to just remove it. Also, the common thing that we found in our dataset are elongations, which is like when you have a scene and the scene is elongated as tatweel. So they write scene and it's actually a character that they add on it. So we remove this character. We intentionally left the English character and English words, because if you like have an article talking about Facebook and they mention Facebook in English and they don't translate it in Arabic, so if you remove it, you're removing actually information from these articles, from these sentences. So we decided to keep it there. Also, I think it's better when you use it with other domains, and if you encounter some English data in it, the model will have some kind of very small understanding of English. We generated the training data and we stored them on a Google bucket. It's a lot of training data. It's 700 gigabytes of storage.
Wissam,
yeah.
Sorry to cut you. Did you remove those things because they were noise, or you removed them because you did not find any good use of them?
You mean the elongations?
The diacritics or
they added, like, a diacritic is actually a character, so they added a lot of variations on these words. So you can consider it noise, you can see it as a noise, or not very useful information. So if as a human you can understand the sentence without diacritics, that's fine. Why do we need to train on them? And if we trained on them, when you do fine tuning and when you do predictions, you have to have them. But we're trying to match between the training domain and the fine tuning domain.
But let's say you left some room for other people to use them and have a paper published.
Yes, you can say that. Maybe they can try it and they tell us if they got a good, better accuracy. I don't know. I think it won't add a lot, but it's good. It's good if you remove them. Maybe if we kept the shadda, maybe it would be good. But
I kind of disagree that they do not add any value. I mean, many times they add, not a lot, but really sometimes you need them to understand the verb or some.
Yes, true. But generally,
that's why removing them in the first time is good. But then I think for further researchers, they might need to investigate how can these things make difference.
They will have to find a way to remove only the diacritics that don't add information. So it's a good research problem, honestly. What diacritics are necessary to understand, or what diacritics that are necessary that they don't change the meaning of a sentence. Some diacritics does change the meaning of a sentence.
I mean, this is one of the most important aspects of Arabic is to have this haraka and shadda and all of that. So, anyway, I don't want to take the whole time.
That's fine.
Keep going, yeah.
So the training data, after we have to generate this training data. So we have to get these sentences, mask them, do the next sentence task, so where we randomly replace sentences. Also during training, on the first 90% of the steps that we did, of the first 90% of the 1.2 million steps that we did, we trained on a sequence length of 128. So it makes the training faster and generally we don't have a lot of sentences that are 512, which is the max sentence length that we have. So we only trained on 128, and after that we generated new data for sentence lengths of 512, and we used that just to make the model learn about we call them the positional embeddings. I skipped them today, but these are also a good contribution in the transformer architecture, the positional embeddings. So we wanted to improve on the original BERT segmentation by doing pre-segmentation, which is Arabic-specific segmentation. And why did we do that? We did that because when we first generated our vocabulary, we found out that some words are repeated twice. And by repeated twice, I mean, let's take the word sayaktub here. The sayaktub word will have to appear twice. Once as yaktub, and once with hashtag yaktub, because that we might append a prefix for it, like alif ta'arif, sa, wa, fa, ba. So why waste space in our precious vocabulary? Because our vocabulary is limited. Why waste space in this precious vocabulary to have duplicate words? Instead of just having one word and alif ta'arif as another word. So this is our yes.
Wissam, how did you deal with word, flower, and waradda?
Oh, this because we removed the shadda here. This will introduce some ambiguity. But I think from the context of this sentence, ورد and ورد, they don't usually come with each other. But from the context of the sentence, the model should be able to understand that we're talking about ورد or ورد. Sorry.
I want to ask you about how to evaluate tokenization in general. So I want to to decide what is the best tokenization approach. Do I have to train the whole model and fine tune it to see the accuracy?
To do that, usually with BPE tokenization, they do sometimes it's called information compression ratio or something like that. Because you're trying to compress all this it's like if you're familiar with the way we compress files, so you're trying to find the best way to compress all this knowledge into smaller size. So that's the intuition behind BPE. This is a number to do. So if you can find the compression ratio on all the articles that you have, and this takes time, but but it might reflect the real life performance of that model after training. But to make sure that it is better, you have to train it. So we did to prove that this was better. We had to do the training to show that it was better. And here you can see our results. Compared the the V1 is the one that uses segmentation, and the V0.1 the one that doesn't use segmentation. So we just get the words and then do word piece on them. Also here we also do word piece after we do segmentation. So I think we might find some words that we don't have after segmentation that we don't have in our vocabulary. So then we apply word piece on them, so that we don't have any out of vocabulary words. So if you compare the numbers, they are almost all better than multilingual BERT by a good margin. AraBERT, the only place where AraBERT V0.1, the one that doesn't use tokenization, does better is in NER tasks. Why? Because in NER we usually label we use the label of the first token as the label of the whole word, because we had to do splitting either in word piece or either in using key segmentation. So if let's say this word starts with alif ta'rif, the label of alif ta'rif doesn't carry much meaning than the label of the word al-kitab, let's say kitab. So this is an intuition behind why the non-segment, when we don't do segmentation, we get better results. And this is the only case where segmentation, that we found that segmentation actually had worse performance. And in other cases, the first 5 are sentiment analysis. The results are close, but we got this is like the average of the results. So we did multiple runs and we averaged them, and it turned out that the AraBERT V1 was better in most of them. And this one is name entity recognition, and the last one is question answering on Wikipedia. And this is where the pre-segmentation shines, because the first data sets are all dialectal Arabic, and segmentation on dialectal Arabic has some errors and doesn't work very well, but it's still better. It's still that good. And when we do question answering on Wikipedia and the ARCD data set, we got way good, better performance, way better than the multilingual BERT. In the paper, we have here the results as 30, but we later figured out that we had a bug, and we trained again, and we got a great improvement in the results. Also, when you compare them to previous state-of-the-art, these state-of-the-art are, these ones are all on the ULM fit for Arabic pre-trained model. So the transformer-based model was able to beat the LSTM-based models. And this model by Dahu, I think it is on the Jordanian data set here. I think it was a CNN-based embedding model. We also matched the performance. and sometimes sometimes we got better performance, and sometimes with lower performance than the best state of the art. So these are all maybe models that are specifically made for these data sets. And you can get pretty close to state-of-the-art or state-of-the-art results using just AraBERT, which takes like 5 minutes to train when you do fine-tuning. I will show you a little bit how to do fine-tuning. So what's next? What's next for AraBERT? The next thing we should try is we should find the performance of BERT large. So our model is based on BERT base, so we need the performance on BERT large, but it is more resource intensive. And maybe we can move from the BERT model, the pre-training tasks, to a better models, which are ALBERT and the new released Electra, maybe Roberta. We also, for Arabic language, we don't have generative models. So as far as I know, transformer-based generative models, we don't have them for Arabic. So this might be a next step for us. Also, in Arabic language, we have too much dialects. So these dialects are split into groups, and each group has its own unique vocabulary and unique sentence structure. So maybe an AraBERT that is trained on dialect, maybe this is a solution. Or maybe we can find a way to reconcile between MSA and dialect. So this is also a research question. And then I will move now into the demo on Colab. So my first demo will be on using the TensorFlow Estimators architecture, and this code is provided on our repository, and it's based on functions in our repositories, which are based on functions from BERT. I also here's another demo that it's a code that I made on using the PyTorch API with the Hugging Face, also a Hugging Face API. And recently, Hugging Face released a trainer API that trains your model easily, but it's just very recent, like four or 5 days ago. So I'm working on making a demo of AraBERT using this Hugging Face trainer that supports both PyTorch and the TensorFlow. So it makes it easy to train AraBERT on your own data. There are some libraries on GitHub that supports training directly, but not all of them are compatible with AraBERT v1 with the pre-segmentation. Because when you do pre-segmentation, we are inserting the word, the letter plus, the character plus. Let me zoom in here. And this letter plus, if you feed it again into the BERT preprocessor, it will split the L and plus as 2 tokens. So to fix that in the transformer library, you have to feed with them the never split token. You have to feed with them the tokens that should never be split, which are imported from the preprocess _AraBERT file. And these are the same tokens that Parallel segmenter use. So these are the prefixes and the suffixes. So you have to pass the never split here, else the model will the code will split the plus into two tokens. This is for AraBERT v1. The AraBERT v0.1 doesn't need that. So here is an example of let's say Walan Nubalir, because we don't have it in our vocabulary, and Farasa segmenter didn't split the noon, so it left it as Nubalir. The word piece tokenizers split the word into Nubal and the letter Ghain. This is one way. This is the way that the v1 architecture works. The v0.1 has again no pre-segmentations and will do word piece tokenization on all the characters. So here, let's say the word al-maktab. If you look at the vocabulary, we find the word al-maktab, and also you'll find the word hashtag maktab, and you find the word maktab. So these are 3 words for the same basically the same word. And let's see here the word zamanuna. So it's split into Zaman and Nu and Na. It's automatically split here. But if you look, so it took 3 places into in the sentence tokens. If you look at the parasite tokenization, we only take 2 places because we have the Na, the plus Na as a suffix, and we have Zaman as a whole word. So not all libraries support this never split tokens. So watch out when you use them. I think that there's a library called FastBERT. I'm not sure. I don't think they support it. So make sure the libraries support this before using AraBERT v1, or if you want, just use the AraBERT v0.1. And both of these models are available on Hugging Face. Let me get them. And it will be downloaded easily for you. So that's a tokenizer equal auto tokenizer from pre-trained, and you give it the path to our model, which is on the AUB Mind Lab, the V1 model and the V0.1 model, which is V01. So now let me move into the demo. Demo, I will just go over the code that we have on our GitHub repository. It's the code that allows you to train a sentence classifier using TensorFlow. And here I'm taking as example the Arabic Jordanian Twitter for sentiment analysis. So the code supports both TPU and GPU. Here I'm selecting GPU because if you want to run it on TPUs, you will have to have your model on your Google bucket storage. So make sure the runtime is on GPU. And recently you have to run the TensorFlow version 1.x, convert the TensorFlow version on Colab to 1.15 instead of TF2 version. Check which GPU that you have. You have to check the memory that you get, because the memory gives you how much the batch size. And today I got lucky. They gave us a 300, an NVIDIA 300 with 16 gigabytes of RAM. So we got lucky today. Usually they give you a 12 or a 15 gigabytes of VRAM. So that's a T4 or a K80, I think. I saved my model on my Google Drive. So if you want to get them, you go into our AraBERT GitHub and you find them in the table here. The TensorFlow version are on Google Drive, so you just copy them to your own Google Drive and start using them. Also, the PyTorch are available again on Google Drive and on Hugging Face repository. So let me sign in to my Google Drive. And copy the AraBERT version that you want to use to your Colab instance. So I'm copying it from my AraBERT models repository to my instance here. And you'll find it under the folder tf_AraBERT. You also find the vocabulary, the config file, which contains all the parameters that we used for AraBERT. We have 12 hidden layers. Max length is 512 tokens. Hidden size 768. 64,000 vocab size. And you can also see the vocab size, the vocabulary that we have. And here, let's skip through that. So you can see that we have full verbs and full words, and we also have the hashtag. These are words that are common in the dataset that we use. What is it? And here. So this is hashtag juzr. It's not the juzr hashtag, but the formatting is weird when you mix English characters and Arabic characters. So this is the vocabulary. We also left about 4,000 unused tokens. So these are at the end. So about 4,000 unused tokens that you can only replace with your own. If you have like words from your own domain and you know them, just replace them here and run few pre-training steps. Or the author of BERT recommends that says that you can also not do that, and the model will try to understand on its own without replacing them. But you can try it and tell us the result when you do it. And this is the vocabulary. So it's 3,900 empty vocab, unused vocab. If you want to get the Farasa segmented, you just go to this app, to this link, register, and they will give you the Farasa segmented because it's not, I don't think I'm allowed to share it on my repository. So I'll copy it from my drive. To use Farasa, you need Java, so you will, this function here installs Java on your Colab system. It will also install Py4j to open a Java gateway, and it will also install PyArabic for some cleaning and some functions that we use in our Arabic pre-processing. Yeah, it's copied to here. Sometimes the Java runtime will hang and will give you error, so you can run process kill Java to kill it. We are trying to fix this issue, but this will work. Now let's clone the AraBERT repository. And here I will show you how segmentation works. So I'm importing the tokenization from AraBERT. I'm also importing the preprocess function from the preprocess underscore AraBERT file. I'm also opening the gateway, a Java gateway, which I give it the path of the Farasa segmented. Make sure the path is correct. So the path here is where am I? Where's the Farasa segmented? Because if you don't do that, it will give you errors. Opening the Farasa and setting the AraBERT path, which is the path to where the checkpoint files are. So I'm initializing a BERT tokenizer from the vocab file that we have. And now let's do some text pre-processing. So let's take the phrase الدراسات النظرية للتصاميم الحديثة والمتطورة. So الدراسات was split correctly, النظرية was split correctly. للتصاميم here التعريف was added. So Farasa was able to add التعريف here. الحديثة والمتطورة. So again, if you don't have, let's say, متطورة and the vocab, you have muta and hashtag تطور. Maybe you have it like that. And now let's do tokenization. Here you can see nothing has changed because we have all these tokens into our in our vocab. Make sure again the GPU runtime is enabled. I linked here the paper that published the Arabic Jordanian dataset, Twitter dataset, against the sentiment analysis dataset. Append BERT to your system path. Here I'm going to use the modeling function from AraBERT that gives you the model, optimization function, the tokenization already did it for above. And from because we're running classification, we need to import the input function builder and the model function builder from the run classifier file. There are files here that have run pre-trained. If you want to run question answering on Squad, if you want to just extract the features, there are files that already exist here and you can easily use them. We will use the train test split from sklearn to split the model. And this segment here, if you have TPU, it will initialize the TPU. It will initialize the TPU and will set, it will get the TPU address. If you don't, it will just run on a GPU. So you don't have to do anything here. Now let's import our data using pandas. It's an Excel file, has a text column and a label column. So it had a feed column and a sentiment column. So we label them as text and label, and now we apply the preprocess function on our text. To do preprocessing, since the preprocessing is the same for AraBERT and AraBERT v1 and AraBERT v0.1, with the only difference is that do Farasa tokenization is false for the 0.1. So if you want to use the v1, make sure that do Farasa tokenization is true, and you pass it the Farasa gateway that we defined above. Because if you set this to false, it will not do anything. Just clean it. But this is already clean. So keep it true. After that, we're calling the input example function from the run classifier file. This will convert our text into input examples that can be fed and that can be transformed into features. The global unique ID, we don't need it now. It's not used, so we have to leave it as none. The only thing that we use is the text A, which is the first sentence. And we don't have a second sentence. We don't have a second passage. So it's just a single sentence classification task. So we're only using one sentence. This is why we have text A only. Text B is none, and we provide the label. We run this on our training and testing. It's a small data set, it should run fast. And here we are converting these examples to features. And let me show you how the features will look like. Max statement is not defined. Where should we define that? Oh, I think it's defined here somewhere. Oh, max length. So I'm using a max length of 128 instead of the full one because we are using GPUs and we have less memory than TPUs, and they generally don't fit. And then you will fit. You'll have your smaller batch. You have to lower your batch size. So instead of doing that, just lower the maximum sequence length and then make your batch size higher. Because not all the sentences are long, so some of them are really small. So here you can see that al-aqida, the word aqida, we didn't find it in our vocabulary, so it was split into multiple ones. Also, Farasa segmenter here failed to get al-ta'rif plus. So the word feast tokenizer handled this failure. The input IDs are the IDs for the index IDs for the vocabulary. The input mask here is just where we have label, where we have tokens, and the rest are just zeros because the sentence is short. And our label. Segment IDs is all zero because it's just one sentence. We don't have two sentences. And this is an example of this is the training data that we are feeding BERT. And it will take the embedding of the CLS token and will do classification on top of it. And this is all handled by the Estimator API that is provided by the library. Our training batch size, let's put it as 16. I'm not sure if 32 can fit on our GPU, but let's keep it to 16. You might also have to change it to 8 if they give you a lower size GPU. The max sequence length is 128. Already said that. Again, the learning rate it's a big factor in the training. Generally, you can try it between 10 minus 5 and 6 times 10 minus 5. I found these to work the best. So you have to optimize this. And the model doesn't need more than 6 epochs. I say 6 epochs are usually within 2-3 epochs. 4 at max, the model will converge. So you don't really need that. You have to have some warm-up for the learning rate. And if you have TPU cores, there are 8 TPU cores, so you will use that if you have TPU cores, you don't change it. Also, the predict batch size is the same. Here I'm loading the config file from the AraBERT repository, from the AraBERT repository. I'm loading it into the BERT config file. Again, the config file contains the parameter, how many hidden layers we have, how many attention heads we have, what is the vocabulary size. So this is all needed to initialize the BERT model. So we run that and we should have here output printing. If you don't, then something is wrong. This is just a check to have that everything is correct. Since we are training for 6 epochs, so these are 6 times, we have to find how many training steps we have. To find out how many training steps we have, we just divide how many training features we have by this, the batch size. So we get how many training updates per epoch. Multiply it by the number of training epoch, you get how many total training steps that we have. Again, multiplied by the warm-up steps, which is 10%. So the first 10% have higher learning rates. And you get, here's to calculate how many steps per epoch. So just the same question. After that, you feed the config into the model builder. Also here, you have to find out how many labels do you have. Here we have positive and negative, so these are only 2 labels. We provided with the initial checkpoint, which is here the pre-trained Arabic checkpoint. So if you want to continue training on your own fine-tuned data, you have to provide it here. Learning rate, we give it to the model function, we give it the number of training steps. And if use TPU is true, which should be automatically set if you have TPUs, it will get passed. Also, this will get resolved on its own. Parameters that are important here are the keep checkpoint max parameter. Set it to 0 if you want to keep all the checkpoints that you are after each number of steps. So if you set it to 0, it will keep everything. If you set it to 5, let's say, we'll just keep the last 5 checkpoints and we'll delete the rest. You give the training batch size and the eval batch size to the TPU estimator, it will also run on the GPU, so it's fine. Yeah, it runs on CPUs and GPUs. It's fine, it runs on everything. And you have to give it the training input function and the testing input function for the evaluation. The only difference between these two are is training parameter. So if it is training, because you have the labels in it, and it tells the estimator that it's training time now. So let's run this. Yeah, we have 540 steps and 90 epochs per steps for times 6. It's 560 steps. And let's start the training. The training should be fast. Here it's initializing the model, getting the training variables from the checkpoint. So all the layers are initialized from the checkpoint. There are 12 layers. It's only the last output weights layer. This is the classification layer. Isn't initialized from the file because this is the layer, the classification layer that we add on top of the BERT model. After that, it will start running the training. So this should take about 5 minutes. I will leave it running and I'll explain the evaluate function. Using the TPU estimators, well, I found it hard to do evaluation while training. I couldn't figure it out. They have a train and eval function, but it didn't work. So after finishing the training, we run evaluation using all the model files that we have. And this is just a loop that I wrote to look over all the training files that we have, and it will run the estimator.evaluate function. Now we are running on 3.5 steps per second, so this is 550 over 3.5 of few minutes. In 2 or 3 minutes we are done. First epochs finished. Before that, I think the estimator is used to provide the loss function in the output, the loss value in the output, but now it doesn't. So it's fine, we will visualize them later. After finishing the training, you will find here a folder, the fine-tuned model folder. It will contain all your fine-tuned models that we will look over it. will also contain the events file, the TF events file, which contains all the parameters that we have it during training. It will contain all the metrics that we have during training, which we will give it to the TensorBoard TensorBoard extension, so it shows us the output. In a few minutes, and we're done. So if you have any questions now, feel free to ask me.
Wissam, I have another question. I have a question.
Yes, yes.
How will BERT handles the imbalanced training data, especially for the fine-tuning tasks? Let's say for classification, like example.
Inherently, it doesn't have anything to deal with it. But when we tried it, we had pretty unbalanced data set. We tried it in the offense eval, I think it's offense eval competition, where we had, I think it was 80% negative and 20% positive values. And we even had one with 10% positive values and 90% negative values. And it got good results. We tried to improve on it using other sampling techniques to fix these balance issues, but it barely improved on the initial results that we had. So I think it handles them well.
Nice, thank you.
Now I'm running the evaluation on all the checkpoints that I said that we have.
I have a question if there is time.
Oh, yes, you have time.
Yeah, I'm curious, how much did it cost to train the BERT model from scratch?
Good question. I forgot to tell you, but it cost us $0 because you can to use TPUs. You can apply for a TFRC grant. So they give you TPUs for TFRC TensorFlow. They give you free access for TPUs for 1 month, and they give you, I think, 5 V3 TPUs and maybe 100 V2 TPUs. So since I'm in academia, they gave me an access for 1 month, which was enough for us to train BERT. Also, if you don't have access to the TFRC program, we initially tried training BERT on Colab, using the TPUs on Colab. The issue with it is that it times out every 12 hours, I think. So every 12 hours, you have to just go wake up and restart again training, but it works the same. And where you have issues in the cost are in storing this data on the Google Cloud. So when you store 700 gigabytes on the Google Cloud storage, it will have, I think they cost like $2 per 100 gigs or $3 per 100 gigs. So this is where the main cost is. And we got around that by creating a new Google account where they give you $300 to play with. It was more than enough to train them.
Yeah.
So if you want to train, you just need, I think, $500 maybe for the storage. If you use 3 TPUs. Because TPUs are expensive. They cost like, I think, $4 per hour on the preemptible ones. Now we were getting accuracy around 93, which is pretty close to what we got. We were 93.8.
If we would train this model, yeah, please. If you would train this model on GPUs, how much time?
On GPUs, you will need a GPU, multiple distributed training on multiple GPUs, because the model is very large. So a GPU, let's say you have a V100 GPU is very expensive to have. If you have one, which is great, it's like $5,000 per GPU, and it has 32 gigs of memory. V2 TPU will have 64 gigs of memory, so it's even less than a TPU. So you need, let's say, 2 GPUs, and each GPU will cost you, I'm not sure how much per hour, but it will cost you almost the same, and it's slower than TPUs. And you'll have to do some distributed training parameters. So you have to play a bit with the code to make it distributed. I think the Hugging Face repository have good good code for pre-training BERT on TPUs and on GPUs using PyTorch. So it's it will work. Here you can see the evaluation accuracy that we have only after the first epoch. So this is the start at 0. So after the one epoch, we already got 90% accuracy. And then when we go throughout the epochs, it's varying around 93 in the fourth epoch, maybe. We got 93% accuracy. So the model learns very fast. This is the powerful thing that was introduced by transfer learning. So that's it.
Hello, Wissam. Thank you for this presentation. Going back to the cost, I want to ask what would be the cost to train AraBERT large? And could we consider training on social media data like a huge collection of tweets?
What would be the cost? The storage cost will be the same. The training costs will be, if you get a TFRC grant, it will cost 0, so you wouldn't need a lot. But the only problem that I can see now in this is that training on social media data like tweets, tweets are not documents. So if you want to do the next sentence prediction tasks, you cannot do it. So either you turn it off, or you try to find another way. But the next sentence prediction won't work. Also, these tweets are generally short. So tweets are like limited by, I don't know, 250 characters. So let's say 20 or 25 words. Split them into, let's say, multiple tokens, maximum 50 tokens, let's say. So 50 tokens is well below the 512 maximum sequence length that BERT gets. Thank you, Zaid, for your comments. Thank you, Ali. Thank you, Rad. Rad asking, what next steps will increase accuracy in your opinion? There are generally the new models use a bit of different pre-training techniques. So the AraBERT model doesn't use a next sentence prediction. It actually uses sentence order prediction, which the authors argue that it makes the model learns better the relationship between sentences, because in the sentence prediction task, they argue that the model isn't learning that sentence 2 is after sentence 1. The model is learning that the sentence 1 and sentence 2 are from the same topic. So when you introduce a sentence order task where the model has to predict which sentence came first, this is a better way. Also, there are approaches that uses different inside variations of the models, like XLM, which is cross language modeling. It tries to find hidden masks between it tries to mask words between two languages, so two sentences, each one from a language. So this is currently a good research area. It's every day you have new models that claim better state-of-the-art results. Did I answer the question? No, Saleh. Is it feasible to use BERT or AraBERT for text summary generation? So since to do generation BERT, you cannot directly use it for generation. You can do maybe sentence importance ranking, and based on that, you pick the most important sentences, but you need a specific data set for it. Or a good approach, maybe try to look at the Hugging Face library and how you can use a decoder based on BERT. This is more advanced stuff. So you try to initialize a decoder using BERT and train on the decoder on generating some new summaries. But like this, you cannot use it for summary generation. Thank you, Joe. Thank you, Noof, again. Tara is asking, what is the inference speed for online serving? Okay, inference speed. If you use it from TensorFlow directly, I think it's around 200 milliseconds. But there are libraries like the ONNX library from Microsoft and the TensorRT library from NVIDIA that makes it faster. Also, there are implementation in C++. So if you're brave enough to find, and you have time enough to convert this to C++, go ahead. It will reduce it to 17, I think 17 or 20 milliseconds on a CPU. Is good. Is what's achieved with ONNX from Microsoft and from C++. Yusra is asking what tasks that prove to not suit BERT and what are the alternative approaches to tackle. Generative tasks are usually not, we don't use BERT for it. And all classification tasks that ISO can use BERT for it somehow. So generating stuff is out of the, not out of the question, but it's not intended. And yes, Zed is saying that there is mobile BERT that can run in the browser. Yes, mobile BERT is an optimized way of BERT. Also, there are approaches that do knowledge distillation on BERT. So they try to create a new model that learns the initial model, and this new model has less parameters. So it's faster on inference. That's it, I think. Also, there is head pruning, so you can remove some of the heads, but these are all theoretical and research work. So it needs some time to figure it out. If you want to get back to the discussion on the training data, when we got Wikipedia from the dumps, we used our code, our existing code from our previous language model. You can find it on our AUB Mine library. On the Hulmuna model. The Hulmuna is a ULM fit-based model trained by Obaida, or my colleague. And in it, you will find, I think here, a Wikipedia extractor py. You can use this to extract the articles from Wikipedia. And for the news, I was saying, I think the 1.5 billion corpus is the biggest one that we use. We also got the web scraping websites from the Web Archive. So Web Archive, the Wayback Machine. And we used the ASEAN corpus. By the way, all the details are available in our paper. So if you go into AraBERT, you can find our paper here, and you'll find all the details about the pre-trained data and all the hyperparameters and the explanation of unique stuff that we did. And that's it.
Thank you, Wissam. Thank you for presenting this interesting work. It's nice to see the mark of Arabic linguistics in modern day approaches, such as yours. And we always like a favorite.
Hopefully we can do better again with the Arabic language.
Inshallah. We've seen few questions throughout the talk, and I'm sure there's more hiding.
Yep.
So